For the first time ever, scientists have used lasers to redirect lightning toward a safe target. The experiment, which took place atop Santis Mountain on the northern edge of the Swiss Alps, is the first real-world demonstration that intense bursts of light can be used to fish for lightning from storms and redirect it to a safe location. Scientists have previously used lasers to bend the path of electricity in the lab, but achieving this outside is challenging. After hauling their laser to Santis summit at an altitude of 8,200 feet, 2,500 meters, the researchers fixed it to a 407-foot tall, 124 m, transmission tower there and pointed it at the sky. Then, by firing the infrared laser at passing storm clouds in short blasts of roughly 1,000 times per second, they corralled a path for lightning to hit the tower 4 times in 6 hours. The researchers published their findings January 16th in the journal Nature Photonics. Although this research field has been very active for more than 20 years, this is the first field result that experimentally demonstrates lightning guided by lasers, the researchers wrote in the study. This work paves the way for new atmospheric applications of ultrashort lasers and represents an important step forward in the development of a laser-based lightning protection for airports, launch pads, or large infrastructures. Lightning emerges when atmospheric static electricity, generated by the friction of ice clumps and rain in storm clouds, separates electrons from atoms. The negatively charged electrons then pool at the storm cloud's base and attract positive charges from the ground. As electrons steadily accumulate, they begin to overcome the resistance of the air to their flow, ionizing the atmosphere below them as they approach the ground in multiple forking and invisible leader paths. When the first leader path makes contact with the ground, electrons hop to the Earth from the point of contact, discharging from the bottom up in a flash of lightning, called the return stroke, that travels to the top of the cloud. Lightning rods shield buildings by providing leader paths with a quick and safe route to discharge electrons into the ground, but the area they protect is limited by the rod's height. To get around this limitation, the scientists beamed their powerful laser bursts at the air near the rod, tearing electrons from air molecules and sweeping those molecules away to create an electron trail between a nearby storm cloud and the rod for the lightning to travel along. Sure enough, strikes hit the rod during the 6 hours of the laser's operation, easily surpassing the usual frequency of strikes on the rod of roughly 100 times per year. Even more direct evidence of the experiment's success came from one of the strikes that was captured by cameras in slow motion as it zigzagged onto the path cleared by the rod. The scientists now want to replicate the effect in other locations with different atmospheric conditions, rods, lasers, and pulses to see if this approach could be deployed more widely, and if lightning might strike twice. Powerful laser blast used to control lightning for the first time. Lightning discharges between charged clouds and the Earth's surface are responsible for considerable damages and casualties. It is therefore important to develop better protection methods in addition to the traditional Franklin rod. Here we present the FRST demonstration that laser-induced flamets, formed in the sky by short and intense laser pulses, can guide lightning discharges over considerable distances. We believe that this experimental breakthrough will lead to progress in lightning protection and lightning physics. An experimental campaign was conducted on the Santis Mountain in northeastern Switzerland during the summer of 2021 with a high repetition rate terawatt laser. The guiding of an upward negative lightning leader over a distance of 50 m was recorded by 2 separate high-speed cameras. The guiding of negative lightning leaders by laser flamets was corroborated in 3 other instances by very high-frequency interferometric measurements, and the number of X-ray bursts detected during guided lightning events greatly increased. Although this research field has been very active for more than 20 years, this is the FRST field result that experimentally demonstrates lightning guided by lasers. This work paves the way for new atmospheric applications of ultrashort lasers and represents an important step forward in the development of a laser-based lightning protection for airports, launch pads, or large infrastructure. The idea of using a laser to trigger lightning was first suggested by Ball. A first attempt to trigger and guide natural lightning with lasers was made by Uchida et al. In 1999, using a combination of 3 lasers with kilojoule energy to form a 2 m-long plasma spark. In this article, we present results of a campaign relying on the use of laser filamentation. The principle of the filament lightning rod is the following. Intense and short laser pulses are sent toward the clouds. They undergo a filamentation process during their propagation. The laser pulse first shrinks in size because of the laser-induced change of the refractive index of the air, which acts like a self-generated series of increasingly converging lenses. The laser pulse eventually becomes sufficiently intense to ionize air molecules in a high-field process. Further propagation of the laser pulse is ruled by a dynamic competition between beam self-focusing and the defocusing effect due to the presence of free electrons. This competition maintains narrow channels of ionizing laser pulses over long distances. Along these filamentary regions, air molecules are rapidly heated by the absorbed laser energy and expelled radially at supersonic speed, leaving behind long-lived channels of air with reduced density. These low-density channels of millisecond duration have higher electronic conductivity and consequently offer a privileged path for electric discharges. Meters-long electric discharges triggered and guided by filaments have been demonstrated in the laboratory, and they have been shown to compete successfully with traditional lightning rods. The ionized length of filamentation can reach 100 meters when the initial pulse power of picosecond duration is in the terawatt, 1012 W range. The filamentation process can be controlled so that it starts up to a kilometer away from the laser source. It is therefore conceivable that filamentary channels can serve to guide and possibly even to trigger lightning discharges under appropriate weather conditions.